Power engineering, also called power systems engineering, is a subfield of energy engineering and electrical engineering that deals with the generation, transmission, distribution and utilization of electric power and the electrical devices connected to such systems, including generators, motors and transformers. Although much of the field is concerned with the problems of three-phase AC power, the standard for large-scale power transmission and distribution, across the modern world, a significant fraction of the field is concerned with the conversion between AC and DC power and the development of specialized power systems such as those used in aircraft or for electric railway networks. Power engineering draws the majority of its theoretical base from electrical engineering, and while some power engineers could be considered energy engineers often do not have the theoretical electrical engineering background to understand power engineering. History. Electricity became a subject of scientific interest in the late 17th century with the work of William Gilbert. Over the next 2 centuries, a number of important discoveries were made, including the incandescent light bulb and the voltaic pile. Probably the greatest discovery with respect to power engineering came from Michael Faraday, who in 1831 discovered that a change in magnetic flux induces an electromotive force in a loop of wire, a principle known as electromagnetic induction that helps explain how generators and transformers work. In 1881, 2 electricians built the world's first power station at Godalming in England. The station employed 2 water wheels to produce an alternating current that was used to supply 7 Siemens arc lamps at 250 volts and 34 incandescent lamps at 40 volts. However, supply was intermittent, and 1882 Thomas Edison and his company, the Edison Electric Light Company, developed the first steam-powered electric power station on Pearl Street in New York City. The Pearl Street station consisted of several generators and initially powered around 3,000 lamps for 59 customers. The power station used direct current and operated at a single voltage. Since the direct current power could not be easily transformed to the higher voltages necessary to minimize power loss during transmission, the possible distance between the generators and load was limited to around half a mile. That same year in London, Lucien Gorlard and John Dixon Gibbs demonstrated the first transformer suitable for use in a real power system. The practical value of Gorlard and Gibbs' transformer was demonstrated in 1884 at Turin, where the transformer was used to light up 40 kilometers of railway from a single alternating current generator. Despite the success of the system, the pair made some fundamental mistakes. Perhaps the most serious was connecting the primaries of the transformers in series so that switching one lamp on or off would affect other lamps further down the line. Following the demonstration, George Westinghouse, an American entrepreneur, imported a number of the transformers along with a Siemens generator and set his engineers to experimenting with them in the hopes of them proving them for use in a commercial power system. One of Westinghouse's engineers, William Stanley, recognized the problem with connecting transformers in series as opposed to parallel, and also realized that making the iron core of a transformer a fully enclosed loop would improve the voltage regulation of the secondary winding. Using this knowledge, he built a much improved alternating current power system at Great Barrington, Massachusetts in 1886. In 1885, the Italian physicist and electrical engineer Galileo Ferraris demonstrated an induction motor, and in 1887 and 1888, the Serbian-American engineer Nikola Tesla filed a range of patents related to power systems, including one for a practical 2-phase induction motor which Westinghouse licensed for his AC system. By 1890, the power industry had flourished and power companies had built thousands of power systems in the United States and Europe. These networks were effectively dedicated to providing electric lighting, During this time, a fierce rivalry in the U.S. known as the War of Currents emerged between Edison and Westinghouse over which form of transmission was superior. In 1891, Westinghouse installed the first major power system that was designed to drive an electric motor and not just provide electric lighting. The installation powered a 100 horsepower synchronous motor at Telluride, Colorado, with the motor being started by a Tesla induction motor. On the other side of the Atlantic, Oscar von Miller built a 20 kV, 176 km three-phase transmission line from Laufenham-Neckar to Frankfurt am Main for the Electrical Engineering Exhibition in Frankfurt. In 1895, after a protracted decision-making process, the Adams No. 1 generating station at Niagara Falls began transmitting three-phase alternating current power to Buffalo at 11 kV. Following completion of the Niagara Falls project, new power systems increasingly chose alternating current as opposed to direct current for electrical transmission. Although the 1880s and 1890s were seminal decades in the field, developments in power engineering continued throughout the 20th and 21st century. In 1936, the first commercial high-voltage direct current line using mercury arc valves was built between Schenectady and Mechanicville, New York. HVDC had previously been achieved by installing direct current generators in series, although this suffered from serious reliability issues. In 1957, Siemens demonstrated the first solid-state rectifier. However, it was not until the early 1970s that this technology was used in commercial power systems. In 1959, Westinghouse demonstrated the first circuit breaker that used SF6 as the interrupting medium. SF6 is a far superior dielectric to air, and, in recent times, its use has been extended to produce far more compact switching equipment and transformers. Many important developments also came from extending innovations in the ICT field to the power engineering field. For example, the development of computers meant load flow studies could be run more efficiently, allowing for much better planning of power systems. Basics of electric power. Electric power is the mathematical products of two quantities, current and voltage. These two quantities can vary with respect to time or can be kept at constant levels. Most refrigerators, air conditioners, pumps and industrial machinery use AC power, whereas computers and digital equipment use DC power. AC power has the advantage of being easy to transform between voltages and is able to be generated and utilized by brushless machinery. DC power remains the only practical choice in digital systems and can be more economical to transmit over long distances at very high voltages. The ability to easily transform the voltage of AC power is important for two reasons. Firstly, power can be transmitted over long distances with less loss at higher voltages. So in power networks where generation is distant from the load, it is desirable to step up the voltage of power at the generation point and then step down the voltage near the load. Secondly, it is often more economical to install turbines that produce higher voltages than would be used by most appliances. So the ability to easily transform voltages means this mismatch between voltages can be easily managed. Solid-state devices, which are products of the semiconductor revolution, make it possible to transform DC power to different voltages, build brushless DC machines and convert between AC and DC power. Nevertheless, devices utilizing solid-state technology are often more expensive than their traditional counterparts, so AC power remains in widespread use. Power engineering deals with the generation, transmission, distribution and utilization of electricity as well as the design of a range of related devices. These include transformers, electric generators, electric motors and power electronics. The power grid is an electrical network that connects a variety of electric generators to the users of electric power. Users purchase electricity from the grid so that they do not need to generate their own. Power engineers may work on the design and maintenance of the power grid as well as the power systems that connect to it. Such systems are called on-grid power systems and may supply the grid with additional power, draw power from the grid, or do both. The grid is designed and managed using software that performs simulations of power flows. Power engineers may also work on systems that do not connect to the grid. These systems are called off-grid power systems and may be used in preference to on-grid systems for a variety of reasons. For example, in remote locations it may be cheaper for a mine to generate its own power rather than pay for connection to the grid, and in most mobile applications, connection to the grid is simply not practical. Today, most grids adopt three-phase electric power with alternating current. This choice can be partly attributed to the ease with which this type of power can be generated, transformed and used. Often, the power is split before it reaches residential customers whose low-power appliances rely upon single-phase electric power. However, many larger industries and organizations still prefer to receive the three-phase power directly because it can be used to drive highly efficient electric motors such as three-phase induction motors. Transformers play an important role in power transmission because they allow power to be converted to and from higher voltages. This is important because higher voltages suffer less power loss during transmission. This is because higher voltages allow for lower current to deliver the same amount of power, as power is the product of the two. Thus, as the voltage steps up, the current steps down. It is the current flowing through the components that result in both the losses and the subsequent heating. These losses, appearing in the form of heat, are equal to the current squared times the electrical resistance through which the current flows. So as the voltage goes up, the losses are dramatically reduced. For these reasons, electrical substations exist throughout power grids to convert power to higher voltages before transmission and to lower voltages suitable for appliances after transmission. Components. Power engineering is a network of interconnected components which convert different forms of energy to electrical energy. Modern power engineering consists of four main subsystems: the generation subsystem, the transmission subsystem, the distribution subsystem and the utilization subsystem. In the generation subsystem, the power plant produces the electricity. The transmission subsystem transmits the electricity to the load centers. The distribution subsystem continues to transmit the power to the customers. The utilization system is concerned with the different uses of electrical energy like illumination, refrigeration, traction, electric drives, etc. Utilization is a very recent concept in power engineering. Generation of electrical power is a process whereby energy is transformed into an electrical form. There are several different transformation processes, among which are chemical, photovoltaic, and electromechanical. Electromechanical energy conversion is used in converting energy from coal, petroleum, natural gas, uranium, or water flow into electrical energy. If these, all except the wind energy conversion process, take advantage of the synchronous AC generator coupled to a steam, gas or hydro turbine such that the turbine converts steam, gas, or water flow into rotational energy, and the synchronous generator then converts the rotational energy of the turbine into electrical energy. It is the turbine generator conversion process that is by far most economical and consequently most common in the industry today. The AC synchronous machine is the most common technology for generating electrical energy. It is called synchronous because the composite magnetic field produced by the three stator windings rotate at the same speed as the magnetic field produced by the field winding on the rotor. A simplified circuit model is used to analyze steady-state operating conditions for a synchronous machine. The Phasor diagram is an effective tool for visualizing the relationships between internal voltage, armature current, and terminal voltage. The excitation control system is used on synchronous machines to regulate terminal voltage, and the turbine governor system is used to regulate the speed of the machine. However, in highly interconnected systems, such as the Western system, the Texas system, and the Eastern system, one machine will usually be assigned as the so-called swing machine, and which generation may be increased or decreased to compensate for small changes in load, thereby maintaining the system frequency at precisely 60 Hz. Should the load dramatically change, as which happens with a system separation, then a combination of spinning reserve and the swing machine may be used by the system's load dispatcher. The operating costs for generating electrical energy is determined by the fuel cost and the efficiency of the power station. The efficiency depends on generation level and can be obtained from the heat rate curve. We may also obtain the incremental cost curve from the heat rate curve. Economic dispatch is the process of allocating the required load demand between the available generation units such that the cost of operation is minimized. Emission dispatch is the process of allocating the required load demand between the available generation units such that air pollution occurring from operation is minimized. In large systems, particularly in the West, a combination of economic and emission dispatch may be used. Transmission. The electricity is transported to load locations from a power station to a transmission subsystem. Therefore, we may think of the transmission system as providing the medium of transportation for electric energy. The transmission system may be subdivided into the bulk transmission system and the sub-transmission system. The functions of the bulk transmission are to interconnect generators, to interconnect various areas of the network, and to transfer electrical energy from the generators to the major load centers. This portion of the system is called bulk because it delivers energy only to so-called bulk loads such as the distribution system of a town, city, or large industrial plant. The function of the sub-transmission system is to interconnect the bulk power system with the distribution system. Transmission circuits may be built either underground or overhead. Underground cables are used predominantly in urban areas where acquisition of overhead rights-of-way are costly or not possible. They are also used for transmission under rivers, lakes and bays. Overhead transmission is used otherwise because, for a given voltage level, overhead conductors are much less expensive than underground cables. The transmission system is a highly integrated system. It is referred to as the substation equipment and transmission lines. The substation equipment contain the transformers, relays, and circuit breakers. Transformers are important static devices which transfer electrical energy from one circuit to another in the transmission subsystem. Transformers are used to step up the voltage on the transmission line to reduce the power loss which is dissipated on the way. A relay is functionally a level detector. They perform a switching action when the input voltage meets or exceeds a specific and adjustable value. A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by overload or short circuit. A change in the status of any one component can significantly affect the operation of the entire system. Without adequate contact protection, the occurrence of undesired electric arcing causes significant degradation of the contacts, which suffer serious damage. There are three possible causes for power flow limitations to a transmission line. These causes are thermal overload, voltage instability, and rotor angle instability. Thermal overload is caused by excessive current flow in a circuit causing overheating. Voltage instability is said to occur when the power required to maintain voltages at or above acceptable levels exceeds the available power. Rotor angle instability is a dynamic problem that may occur following faults, such as short circuit, in the transmission system. It may also occur tens of seconds after a fault due to poorly damped or undamped oscillatory response of the rotor motion. As long as the equal area criteria is maintained, the interconnected system will remain stable. Should the equal area criteria be violated, it becomes necessary to separate the unstable component from the remainder of the system. Distribution. The distribution system transports the power from the transmission system, substation, to the customer. Distribution feeders can be radial or networked in an open-loop configuration with a single or multiple alternate sources. Rural systems tend to be of the former and urban systems the latter. The equipment associated with the distribution system usually begins downstream of the distribution feeder circuit breaker. The transformer and circuit breaker are usually under the jurisdiction of a substations department. The distribution feeders consist of combinations of overhead and underground conductor, three-phase and single-phase switches with load break and non-load breakability, relayed protective devices, fuses, transformers, surge arresters, voltage regulators and capacitors. More recently, smart grid initiatives are being deployed so that distribution feeder faults are automatically isolated and power restored to unfaulted circuits by automatic hardware, software, communications packages.